Now let's talk about distribution of probabilities. I'll just remind you that we have frequency. It's an estimate of probability in some real experiment, and then we have a probability, which is a theoretical probability. Is it what we expect, the relative frequency we expect in theory? Okay. Then the frequency, the relative frequency, the empirical probability and the theoretical probability are not always the same, of course. But that's not a problem, because if you recall our intuition about the using parametric approach in science, you remember that you have some points and they never ideally represent the theoretical law. For example, if you're talking about linear dependence, your points will always scatter somehow around the line. But it's not a problem, because line still, the theoretical line, so the theoretical function can still represent the behavior of these points quite well. So you have some fluctuations around it, but the major trend can be represented by theoretical function. The same about probabilities. So you have a distribution of frequency, which is a histogram. Or it can be distribution of density based on the frequencies. And then you have the theoretical distribution. And theoretical distribution will not perfectly fit the real distribution of the frequencies, but that's not a problem, because it should catch the major trend, the shape, the position of for example, the center of the distribution, the spread of the distribution, and so on. So if it can fit the experimental distribution quite well, we still can use the theoretical laws. Okay. So let's talk about how to describe the distribution of probabilities, and you will find out that the functions that we are going to use, they're pretty close to the functions or distributions we already learned, like distribution histogram or cumulative distribution, and so on. So any theoretical distribution can be described by three functions. The first function is called probability density function, or PDF. Okay, it describes the shape of distribution, a probability to find a value for each part of some particular range. And the PDF is a theoretical function for the distribution histogram. We will discuss this in a minute. The second function is called cumulative distribution function. And the idea of cumulative distribution function, it estimates a probability to find a value below or equal to a given. Then you again can see that the CDF is a theoretical function for cumulative distribution curve that we have built before. Okay. Then finally, the third function, it's called inverse cumulative distribution function. So it means that it does the same as CDF, but the opposite. So CDF gives you a probability for a given x, and ICDF for a given probability gives you a value. But let's discuss this in some details. So let's start with PDF. Okay. So PDF, it's a probability density function. So it means that it describes the density, the probability density distribution. Okay. So it means that if you, for example, use the density histogram, the PDF will be a theoretical function for the density histogram. Okay. The PDF, that's one of the PDF functions I've created here. So it shows the shape. What it means, shape. It shows, for example, where you have the biggest density. So this is the biggest density, right? So it means that here the values are very, very dense. You have a lot of values in this small range. And then you have fewer values on the left, fewer on the right, and then even fewer, and so on. So the shape gives you where you have the most of the values. Sometimes this peak, if you have this clear peak here, it is also called the most expected values, or the range for the most expected values. We will also discuss that. Now, PDF is not, it doesn't give you exactly the probability, it gives you the density, okay? If you want to calculate probability, you need to find an area. For example, if you want to calculate a probability between the two particular values, let's say we talk about height. So this is height, and then we have 150 centimeters here and 160 centimeters here. So the probability to find a height between 150 and 160, it's an area under this curve within these limits. And from mathematics, we know that area under any curve, under any function, can be found if you use an integral. So the probability to find a value between two is an integral of the PDF function and with these limits, okay. So in this case, it's a good question. What will be the probability to get a value exactly equal to given? Well, that's a bit tricky question, because in fact the probability will be equal to 0. Why? Well, if you have one particular, let's take this is the curve and this is the value, right? The value. So if you take some area around this value, let's say a plus minus dA, where dA is a very small value, okay? So that will be the area, okay? It will be a probability to find a value between a minus dA and a plus dA, a plus dA. Then to get this probability, you need to set dA to 0. And of course, in this case, you don't have any widths for the range. So the probability to find a value exactly equal to given is actually 0. And that's not a big contradiction. Can you find a person whose height is 175 centimeters? I must tell that it's not possible, even though you think that it's very, very simple thing. Well, if you start measuring height exactly, it will be not 175 centimeters. It will be 175 point something. It will never be the same as 175 exactly. So it does not contradict with nature, even though, of course, here we are talking about theory. Here we are talking about purely continuous values. Okay. So once again, PDF is a probability density function. It shows a density. It shows a distribution of probability density. And it shows a shape of distribution. So you can use this function to see where you have most of the values, how big the spread is, and is it symmetric distribution or not symmetric, and so on. If you want to find a real probability, you need to take an integral under a curve using a certain limits, like we did here.